Let us continue our discussion of free real scalar field theory. So I have summarized some of the results that we already have. So here is the action. Okay. And then this is our equation of motion, which you have seen several times. And then the commutation relations are given here. So phi commutes with phi, pi commutes with pi, and the commutator of phi and pi is given by h bar delta cube x minus y. And these commutation relations are at the same time, equal time. We also introduced the Fourier variables last time, the Fourier transforms of the fields, phi and pi. And we also saw that they satisfy the following commutation relations. This commutator vanishes. Similarly, the 2 pi's, if we have a commutator of 2 pi's, that will also vanish. And you get a non-vanishing contribution when you have a commutator of phi with pi. And remember, you get IH bar delta Q K plus K prime. Okay. Then we also wrote down the Hamiltonian density, where the Hamiltonian, let me write as d cube x is curly h, where curly h is called Hamiltonian density. And that we found to be the following: half pi x t squared plus half gradient of phi x t squared plus half m squared is whole square. Okay, we also wrote down, I believe, check. Yeah, this expression. We also wrote down the Hamiltonian in the phi tilde and pi tilde. So let me write down that one also. And you have, of course, the overall factor half pi tilde, but you have a minus kt times pi tilde of kt. And then here we had a term which was omega k square phi tilde minus kt and phi tilde kt, where omega k square is k square plus m square. Okay. Also remember that we had, maybe right here, the momentum density is phi dot. Okay, that's good. Now we are taking phi to be real, and that should have a bearing on the phi tilde. So let's find that out. So phi is real. So if I look at the phi tilde kt, which is just d cube x e to the minus I k dot x phi of xt. Okay. So let me take the complex conjugate of both the sides. So phi is right now being treated as a classical field, not as an operator at the moment. So if I take complex conjugate on both sides, so I get phi tilde star kt d, okay, I forgot 2 pi or 3 by 2 here. This, when you take complex conjugation, will give you a plus ik dot x, And because phi is real, nothing happens to it, it remains phi. So you have e to the I k dot x phi. Okay. Now x is dummy. Yes. Okay. So I can see x is being integrated over, and remember, when I'm writing d cube x, what I really mean is this. It's a shorthand notation, but the full thing is this. The lower limit is minus infinity and the upper limit is plus infinity. Okay. So anyway, let me change from x to minus x. Sorry, that's not what I want to do. I'm sorry. So what I want to do is I want to change k to minus k. So I get phi tilde star minus kt is, so you get a minus sign here, okay, which makes the phi tilde k. So you get phi tilde of kt, okay, or phi tilde star, I'm just changing minus k to k here, and that will make phi tilde of minus kt. Okay. And if you are going to quantize, then you know that star is going to be replaced by a dagger. So complex conjugation becomes Hermitian conjugation, and then you will have phi tilde dagger kt is equal to phi tilde minus kt. Okay, so that's the condition you get because phi is real. So the phi dagger of k is related to phi of minus k, and similarly, if you, the same thing, if instead of phi you had a pi, then you'll get the same relation. Okay, that's good. Now what I will do is I will introduce some new variables, and you will immediately realize why these are so useful. So I define a k t to be 1 over root 2 omega k, square root of omega k, and omega k we have already seen, that's k square plus m square. Okay, so omega k square is k square plus m square. So I have so this is the definition I'm giving, k power minus half, so it's a square root in the denominator, minus k, sorry, okay, that's good. Now if I take a dagger of this, so right now in this equation I am treating phi tilde and pi tilde as operators. Okay, so if I take a Hermitian conjugate of this, a dagger, I put a dagger on that, I get a dagger, which will be this. So omega k is real, so it remains omega k. Phi tilde becomes phi dagger of kt, but our phi dagger of kt is related to phi of minus k, but anyway, it doesn't matter. I can still keep it like this. I goes to minus I. This is real, so nothing happens. And this becomes this. So that's the definition I have introduced. Now it's easy to show the following. And I leave this as an exercise for you. Show that if you take this operator ak and take ak prime, if you find the commutation relation, it will vanish. Okay. Similarly, if you look at a dagger kt, a dagger k prime t, that commutator will also vanish. And if you take a kt and a dagger of k prime t, then of course it will not vanish and it will give you actually h bar delta cube k minus k prime. Okay. So note there is not the iota is not here. So the I is missing. You have an h bar delta cube k minus k prime. Okay, proof is simple that you can easily do. The only thing you would require in proving this is using the fact that pi tilde and let me write pi tilde dagger k t is pi tilde of minus kt, that you will need to use. And similarly for phi tilde, beyond this not much is needed. Kt phi tilde minus kt. So if you use this these two results, then you will be able to show this. Okay, that is nice. Okay. Okay, another exercise. So first you write down the phi tilde and pi tilde in terms of A and A daggers. That is trivial because you have a very simple relation here. You can just invert it. Okay, and if you do so, you'll get the following. And that's not really an exercise. I'm just writing down the result here. So you'll get this A k t plus a dagger of minus kt and I 2 over omega k kt and a kt minus a dagger of minus kt. Okay, please check the results. I hope everything is correct here. Okay. Now one thing I want to do is use this and write the field phi, not the phi tilde, the phi of xt in terms of A and A daggers. Okay, that's what I want to do. So let me do that. So I want to now express phi and pi in A and A daggers. Okay, that's what I want to do. So let's see. Phi xt will be what? You remember it's related to phi tilde via Fourier transform, and this will be e to the I k dot x and phi tilde of k. Now, okay, I should write phi tilde of kt. Now, phi tilde of kt, I can use this expression for that and substitute this. Okay, this will give me maybe I should use the line above. Integral d cube k over 2 pi cube, then e to the I k dot x, and here you have 2 omega k, so that's this factor which comes in the denominator, and you have these two, a k t plus a dagger of minus kt. Okay, I can also slightly modify this. What I'll do is this one is straightforward. There is nothing to be done here. Yeah. Now this one, okay, I think yeah, fine, no problem. So here in this expression, what I will do is I will take k and make it minus k. So I'll do the change of variable from k to minus k. Okay, that I can do because you have an integral over k. So that's a dummy variable. I can do that integral, do that change of variable. Now, if I do that change of variable, this becomes a dagger of kt. Okay, but here you get e to the minus ik dot x. Okay, and what happens here? Here actually nothing happens because of the following. Let me first write down and then tell you why d cube k remains d cube k. So the result will be d cube k over 2 pi 3 over 2. I had missed this. Okay. Then you have a k of t e to the I k dot x, which is fine, plus I have changed the variables from minus k to k in this one. So you can split the this integral into two pieces, right? So each piece has its own dummy variable k. So in that one, in the second one, I'm doing the change of variable, and you get d cube k over 2 pi cube. I will show you why. So this is here, and then a dagger k t e to the minus ik dot x, right? That is what you will get. Now let me show you why this has to work. So if you look at d cube k, that is just this. Okay, the three components of k are k1, k2, k3, and the integration runs from minus infinity to plus infinity. And when I'm saying that I will change the variable from k to minus k, then my k1 goes to minus k1. Okay, that is fine. But then when I do so, then the integration limits also change. So this goes from infinity to plus infinity to minus infinity, right? So when k under k going to minus k, the lower limit minus infinity becomes infinity, and upper limit infinity becomes minus infinity. So that is one thing you get, which is you can write as minus of minus infinity to plus infinity. Okay, so you get one minus sign from here. So these are three, so you get three minus signs when you put it back in this form from minus infinity to plus infinity. And the measure dk1, dk2, dk3, these are three, and each of them is going to become minus dk1 minus dk2 minus dk3. So you get one minus sign here because there are three such factors. So one minus from here and one minus, overall one minus from here makes it plus. So this remains d cube k. Okay, under this change of variables. and that is why I had not bothered about this and only made the changes in here. Okay, so that's the expression of phi. Let me also give you the result of pi. In fact, I want to nicely record them both of them here. We'll use it later. So phi xt is dqk over 2 pi power 3 by 2, and then I had 1 over 2 omega k in the square root. Let's check. Okay, that was missed here. This is this factor. Okay, so you have this one, then a k t I k dot x, and then plus a dagger k t minus I k dot x. Okay, and you can also calculate for pi, and you'll get the following. Have a minus I, because when this guy goes on that side, it becomes a minus I, and then you'll have omega k. So this thing, when it goes here, it will give you omega k over 2 in the square root. So you'll get omega k over 2 square root, and everything else will be the same except for the minus sign. So this will do exactly what it did for phi, and there will be a minus sign. So you will get let me check. Yes, this is correct. So these are our phi's and pi's in terms of A's and A daggers. This will be utilized later. I will give you one simple exercise to do. Show that just a second. Thought I wanted to say something else also. No. Okay. So what you should do is take the Hamiltonian expression, which is already given in terms of phi and pi, phi tilde and pi tilde, this one. So take this expression and substitute phi tilde and pi tilde, which are expressed in terms of A and A daggers. I think here somewhere. Yeah. So phi tilde, pi tilde, you already have in terms of A and A daggers. Substitute that in the expression of the Hamiltonian and show that you get the following. dq k omega k a k t a dagger k t plus a dagger k t a k t. This will be very straightforward exercise, and what I can do is I can write down this in slightly different form. So I will use a dagger a. So what I want to do is I want to keep a to the right, okay, and a dagger to the left. So this term is good, but this term is opposite. So I use the commutation relation, interchange the two, okay, and that will pick up a delta function, because commutation relation will give you a delta function, and which will give us the following. omega k, because it becomes twice a dagger kt, a kt. Okay, so that factor of 2 kills this factor of 2, and plus you will get an infinite contribution because of the delta function. So this half is coming from here, d cube k omega k, and commutation relation gives a delta cube of 0. Okay, because let me show you. Here you have delta cube of k minus k prime. If both k and k prime are same, then you have a delta cube of 0. So that is what you get here, and delta cube 0, and you are integrating over the entire volume in the k space. Okay, so this comes out, this sits outside, it's a delta cube 0 sitting outside, and you are integrating d cube k omega k, and omega k is k square plus m square square root. Okay, that doesn't provide you any damping when k becomes large. So this integral is really going to blow up. So it's an infinite quantity. Okay, because the integration limits are from minus infinity to plus infinity. So this is a divergent piece, but that's fine. It doesn't bother us that much because, see, Hamiltonian, when acts on some state, it will give energy of that state, provided that state is an eigenstate of the Hamiltonian. But then absolute energies do not have much meaning, at least in quantum field theory, the things which we are doing. Okay, so you can always shift the 0 of energy, okay, which is equivalent to saying that I can drop this piece. I don't have to worry about this term. So we will drop this one and write Hamiltonian to be d cube k omega k a dagger k t a k t. Okay, let me emphasize again. I think it's clear, but let me say again. See, this is an infinite amount of, at an infinity, but what really matters is differences between energies. Okay, so if only differences matter, then you can choose 0 of energy to be wherever you like. Okay, and that freedom gives you the freedom to drop this piece. Okay, so we can drop this piece because where to choose the 0 of energy is up to us. So once we are chosen for the entire system, we are fine. Okay, so that's infinite constant, and I have this as the Hamiltonian. Now I want to do one more thing. Let me say this. You already know that energy by itself, or energy, is not a Lorentz invariant quantity, neither momentum, but they together form a 4 vector. So neither energy is invariant. It doesn't have a good Lorentz transformation property, nor the momentum has, but the two together have very nice property under Lorentz transformation. They transform exactly as a 4 vector transforms, and that's why these 4 quantities E, P1, P2 and P3, they are written as P mu. Okay, so that's a 4 vector. Now the energy you are going to obtain from the Hamiltonian, okay, some operator will give you the momentum. So you will have states which will have some energy and they will have some momentum in your theory. And if the Hamiltonian operator is going to give the energy, then there will be some operator which let's denote by capital P, which we will call momentum operator, and put a arrow, so that it's 3-dimensional, which will give the momentum of that state. Okay, so you expect on the basis of relativity that these four operators H, P1, P2 and P3, whatever that P is, okay, that they will together form a 4 vector. So you expect a new operator P mu, which will be this one. Okay. Now we have already derived an expression for the Hamiltonian, which is this, and you see this piece is k square plus m square omega k. Okay. Now if you think of a free relativistic particle, then if it has a momentum small k, okay, then this will be the energy of it. Okay. Now with this in mind, it's easy to guess that the momentum operator P would be the following. So all this will remain the same. And here, instead of omega k, which is this, I would expect to have k. Okay. Now I will do it at a later point of time properly. I will show you how to arrive at this. In fact, we will find all the operators start from Noether's theorem. Okay. But here I just want to make this note so that I can still make progress without taking a digression to Noether's theorem and related topics. So this is nice. Now we are almost going to begin to write down the states in this free field theory. Okay, using and we'll look at the energies and momenta of those states. So I'll stop here this lecture and we will continue in the next video.